I want to talk about MCMC inference part 1 and 2 and Swendsen Wang proposal distribution. First I'll do the easy part, which is the MCMC inference part 1. This function takes an argument called trans name, which is the transition model name, and then so it can be either a Gibbs or MH uniform and so on and so forth. So based on what is passed, they are already provided this code for you. You put at the rate for Gibbs, for example, you say at the rate Gibbs trans and then assign it to trans. For MH uniform trans, you say at the rate MH uniform trans, and that's already assigned to this variable called trans. Now what you have to do in part 1 is you don't have to do anything here or here. Let's scroll down a little bit. Here they have already given an example, right? So if I have function foo of bar, then what I can do is I can put at the rate sign in front of foo, assign it to a variable called foo2, and then I can use foo2 to calculate to call that same function. So this one is same as this one. That is same as this. So since at the top you have this trans, all you have to do is call that, use the trans, pass appropriate argument, and you will get the A back. So you make sure this is most important. You assign that to A. You update A first, and then you also next thing you update this all samples as well. So that's the MCMC inference part 1. The next thing that I want to talk about is this Swendsen-Wang proposal distribution. So let's try to visualize that. So here, this is a pairwise Markov network, and you can view these. This is like the Isling model where you have where you have electrons and they're spinning in some direction. So here in this figure, these black circles are spinning in one direction, and this adjacent electron white will be spinning in opposite direction. So what you do in the first step is you disconnect edges between nodes with different assignments, meaning you find two adjacent electrons, and that are spinning in opposite directions, and you disconnect them like here, right? And once you do that, you activate edges with some probability Qij and create these connected components like here. So for example, after you disconnect the edges, you activate some edges like this, or this with some Qij probability, and then group these things into connected components. Like this one, even one thing can be a connected component, or these three white ones is a connected component, or these four, this one in green circle in this square can be a connected component, and so on. And then the next thing is what you do is you select a connected component and assign it a different label. So like here, what you're doing is you're taking this connected component in green square, and you're changing the assignments for those nodes in that green square to from black to white. And remember, you haven't changed anything on these other variables, that x minus y. So I'll come to that equation here in a bit. So that's the and this goes on. The whole idea is if you did not have this notion of connectedness, these adjacent pairs are highly correlated, so the Gibbs chain will mix slowly. But just by introducing this third variable, or this notion of connectedness between these two adjacent electrons, you come up with this procedure for changing the state, and this will mix faster and move faster. So here are some equations related to that, and that is A of x to x prime is min of 1 comma pi of x prime divided by pi of x times q of x prime to x divided by q of x to x prime. Okay. Now, so this ratio of proposal distribution, q of x prime to x divided by q of x to x prime, is given by these two ratios, which is the first ratio, c of y given x prime divided by c of y given x. That's called log qy ratio, right? And the second one is the R ratio, which is R of y equals L given x prime minus y divided by R of y equals L prime given x minus y. Now this log qy ratio, I'll show you, that's already given to you. Right here, right after this for loop, you will have that log qy ready for you. Okay, so that part is the first product is taken care of. So what's the next one? This R. So this R distribution, so what is this y equals L prime, and given x prime minus y, okay. So that L is the old value, L prime is the new value. So what is this L, so what is this old value and L new value? So if you look here, you'll see two variables. One is called the old value and new value. So that is your old value, and somewhere down the line you'll see a new value right here, right? So these are the labels, like old label and new label. That is the old value is the L, and the new value is the L prime, right? Now you have to, as part of the exercise, you have to provide this R distribution, okay? So this R distribution right here, you have to provide that R of this R distribution, and they have given you a place to do that somewhere here. So if you scroll, so here in a way for variant 1, you will provide uniform distribution, meaning if my variable's cardinality is D, then the R distribution, so all the values will be equal. You basically would divide by D, and you will get all the same values because it's uniform. For variant 2, you have to use the block log distribution that you have already done in the previous assignment. That's how you get your R distribution. So we got the log QY ratio, we have the R distribution. Now this given x prime minus y, meaning all this, you know how when we were changing this green box, right? The rest of these x minus y variables, none of those have changed from this transition to this transition. So we have all these values now. So we know how to calculate this q of x prime to x divided by q of x to x prime, right? You put that here, and then you are left with this remaining one, which is pi of x prime divided by pi of x, which is nothing but the log probability of joint assignment for the proposed one, divided by the log probability of joint assignment of current A. Okay, that's that ratio. And that you can, you know how to already, if you looked at my previous video, I've already told that you basically calculate using the log probability of joint assignment. Is already a helper method that you can use to calculate those two. So with this, you have all the information you need to calculate this A of x to x prime, right? So you would go down and you implement all those ratios that we talked about in this right here, and calculate the acceptance probability. Now, so I just want to summarize here. So in variant 1, what you have to do is you provide uniform distribution here. You provide block log distribution for variant 2. For both variants, you can use the same formula to calculate that acceptance probability. That leaves us with MCMC inference part 2. We already talked about part 1, and this is fairly easy. Here they are asking you to hardcode the QIJs, the probabilities with which a particular edge is activated. Here in this part right here, when trans name is MH Swendsen Wang 1, this will be 0.5 always. However, if you go here, they're asking you to calculate that QIJ using this formula, which is so this formula, that phi of ij is your edge factor, and you take sum of all the ways where the assignments are same for both u and v. That's what your numerator is, divided by, you loop through different values of u and v and sum all the values. So that's basically taking the entire factor value and summing it up. That's how you calculate the qij, okay, for the second variant. So I think so that's all there is to it.